Hello, my name is Abigail Russ. I am an undergraduate working with Dr. Rivera Hernandez in the GT Planetis lab, and today I'm going to be talking about my research, what I've been doing for the past few semesters, which is simulating mud in Mars-like conditions and basically looking at how mud, or rather mud flows, behave under Mars-like conditions. Now, why do we care about mud on Mars? Well, a little bit of background information. So recently, we've been getting a lot of much higher resolution images of the Martian surface, and we have come to realize that what we thought were once volcanic features may actually not be volcanic features, but rather mud volcanism, because we have thought about the conditions on Mars and realized mud probably behaves a little bit differently in such a low pressure, low temperature, and low gravity environment. Specifically, mud behaves rather like lava flows on Earth do. And so this is kind of relevant because where there is mud, there is water. And so knowing a bit more about where the mud is coming from, where the mud is forming, and what the mud formations look like on Mars can kind of point to the paleoclimate of Mars and seeing where there was water at one point. So some background experiments. We worked with Dr. Peter Broche in his lab at, I believe, the University of London, where he actually began to do some experiments on mud in these low pressure, low temperature conditions. Now, obviously, we can't simulate the gravity of Mars here on Earth, but we got pretty close. And what we saw is what we expected, that the mud in this very low pressure condition behaves a lot like lava. We see lobes, we see cavities, we see voids. And so this kind of motivated us to take a much closer look at the mud in these conditions and start to build up a computer simulation so we can kind of better gauge what this is going to look like. So here's another example of a mud flow on Mars versus a mud flow on Earth, or a lava flow on Earth and a mud flow on Mars. And you can kind of see the similarities between the two and kind of understand our starting point and why we took an interest to this in the first place. So why are we modeling mud and rather just not doing experiments? And basically it comes down to it's really hard to make Mars-like conditions here on Earth. And in a computer simulation, we can actually fine-tune the parameters, get the gravity better, get the temperature better, have wind speeds, and really better simulate everything and get a much better picture of the morphology of mud in these conditions. And to do so, we use this program called COMSOL Multiphysics. Now, COMSOL is traditionally used for engineering, but recently a lot more Earth and atmospheric scientists have started using it for fluid-like simulations. So here is the data that Dr. Broche provided us with. Basically, he took 2 tubes of mud, turned down the pressure. There's a lot going on in this graph. We'll kind of parse through that in a second. Turned down the pressure and watched how the mud behaves. And what he saw was that the top of the mud tubes got a lot colder than the bottom, and that is because of evaporative cooling. In these low pressure conditions, evaporative cooling becomes the dominant cooling force, and we see these bubbles forming and rapid heat loss at the top. And because of rapid heat loss, we get things like crust formations and lobes and volcanic-like behavior in mud. So this is kind of a little picture of the COMSOL simulation. If you're not familiar with COMSOL, don't worry. You don't really need to understand this to understand where I'm going in this presentation. Basically, we looked at a mud-like fluid with certain initial temperatures and initial conditions based off of what we expect the mud to behave like. And so this is the data that we found. As you can see, we see a similar pattern in the top of the tube being a lot colder than the bottom of the tube as the pressure dropped. Here's a little animation of the simulation. Some fun little visuals for you. On the left, we can see the temperature plot, and on the right is the humidity plot. And the humidity plot is relevant because of evaporative cooling. This shows evidence that we are, in fact, observing the evaporative cooling that we expected to see. So comparing the 2 data sets, we see, once again, very similar behaviors. However, it should be noted we don't see them at the same degree. So the Broche experiments done in the lab, we saw a much more rapid drop than in the computer simulations, and that can be due to a number of reasons. Mostly we expected that in our simulation we didn't have any sort of drafts, we didn't have any sort of winds. It was a very stationary environment, whereas in the real world experiment, they had some wind flow within the chamber. moving forward, we have started to try to build up an actual mud volcano in Colloq. Now kind of using this as a proof of concept test, knowing that we can in fact do mud-like simulations in Colloq, we want to build an actual mud volcano. And the first step of that is looking at just a single lobe of mud flowing in these conditions. And specifically, we dropped a 2 centimeter radius little sphere of mud pretty much, and we ran it over a series of conditions, specifically temperature, pressure, gravity, and 3 different viscosities. And this is to look at what parameters actually matter when it comes to mud flow. Is it the temperature? Is it the pressure? Is it the gravity? Or is it the viscosity? And we found a lot of data. We got 16 specific plots, but what's actually relevant from these plots? So, looking at constant viscosity, this is under the viscosity of, I believe, 50 pascals per second, which is, think like halfway between water and honey. And looking at this, we noticed, first of all, that the Earth-like one behaved as we would expect. We saw it drop, we kind of saw it flow a little bit, it formed a bunch of different droplets, and then the Mars one stayed relatively together. It stayed relatively uniform and had this kind of single lobe shape, single lobe morphology, which is what we were wanting to see because, once again, behaves like lava does. So looking at differing viscosities, this is relevant because we don't entirely know what type of mud formed these mud volcanoes, formed these formations. So looking at differing viscosities, we can kind of see what actually, once again, what actually matters. And we, from the data that we gathered, learned that viscosity matters more than we might have thought, because in the lower viscosity, we saw a huge difference between Earth-like and Mars-like conditions, whereas in the high viscosities, they look almost identical. So this is kind of illustrating the points that when we're going to analyze these formations, we need to be taking into consideration what kind of mud was making these formations. And all of this is to say there's a lot more to the volcanic features on Mars than we once thought. So some wider applications. Once again, why does any of this actually matter? So as you can see, the Mars rovers are starting to see a lot of interesting volcanic or mud-based activity, and we want to be able to identify. We want to know what is actually going on, and it kind of can show us some insight into the past oceans, past lakes, past water formations, and also potential astrobiology targets, because where there's water, there's life. And overall, looking at this mud, we can generally improve our understanding so we can better identify mud flows and mud volcanoes and just, in general, what is going on the Martian surface. These are kind of some acknowledgements and sources. Thank you again to Dr. Rivera Hernandez for helping with this, and Dr. Jacob Adler, who is, I don't think he's here right now. Yeah, any questions?
Thank you, Abigail. That was great. Does anybody have any questions? I think we have time for a couple.
So you've investigated what mud flows look like on Mars and how they look like lava on Earth, but have you done any modeling, or has any other modeling been done on what lava looks like on Mars?
That's a great question. So going back to the differing viscosities slide, this is why this is relevant, because lava has a very high viscosity. I believe it's like 200 pascals per second. I don't know off the top of my head. This plot right here is kind of showing how at higher viscosities, factors like pressure and temperature don't matter nearly as much as the lower viscosity flows. So we haven't done any particular experiments with lava, but it's less relevant to understanding the morphology of these formations.
Do you have any current theories as to what the mud composition would be and what the formation mechanisms of these volcanoes would be?
So in terms of formation mechanisms, let me go back quite a few slides. This is kind of the current theory where we see this feeder dike, evaporative cooling, and then general flow in this way. As to the composition itself, we haven't actually started looking into this. This is very new research. We've only really gotten into this in the past, half year, I want to say. So we're trying to first understand the general and then go into the specifics of what the mud composition would be.
All right, are there any other questions? If not, thank you again, Abigail. That was awesome.